Nathan Cruz here again with Carlson Software, Director of the Precision 3D Division. And I'm going to give you a quick walkthrough of adding some culverts to roadside ditches. So here we have, we automatically create a storm event for you. So even though we create many different types of storm events so that you can analyze your surface based on various events and then create reports against those, I'm going to go ahead and switch this to typical US settings, 25-year storm SCS, and I'm going to go ahead and calculate a storm event. And what this does is this calculates a watershed and ponding levels based on 5 inches of rainfall over a 24-hour duration. And so what do we see on the screen? We see lots of data, so we see all different colors of lines and so forth. And I'm going to pull this out just a little bit so you can see the white areas highlight. These white areas are subcatchment basins, and you'll notice on the right hand side as I hover, this is what we call the tooltip area, because we have so much information that we do give you back in real time. We have an entire panel dedicated to tooltips, as well as if you'll notice down on the toolbar, we provide you with the instantaneous northing, easting, and elevation over the surface, and for where the mouse pointer is. And then we also give you what the peak flow rate is at that point based on that current storm. So it's quite easy for you to track along one of these blue runoff lines. And these are basically the longest flow lines that are used to do the time of concentration calculations for these subcatchment areas. So we give you the longest flow line, and then we give you the ability to interrogate the runoff volume in real time as you move the mouse cursor anywhere on the surface. And then to the in the tooltip area, we provide you information about everything that you're hovering over. So in this case, we're hovering over a surface, and we're also hovering over subcatchment areas, so you get all of that data, which includes the peak flow, what the maximum headwater elevation is, the maximum volume for this particular subbasin. And we also show you that we're hovering over what appears to be pond number 18. Gives you the elevation, the maximum depth, the volume of that pond. And then you also notice that we have this tailwater information, which is all empty on these initial calculations, and then we give you the maximum potential volume. And you can see that this pond is actually already filled up. It contains as much water as it ever will. And an interesting way to demonstrate the way that we automatically calculate your pipe size, we also identify all of these yellow sticks that you see sticking up are all of the low points, or what we call the sink points in each subcatchment area. And when we draw pipes, we have snaps to it. So you can draw a pipe from anywhere in the scene, but if you get close to one of these, we have a snap, and it's indicated by this round circle. And so and that ensures that I'm drawing a culvert pipe from that low point. And I'm going to go ahead and just poke this culvert through, and what you notice is that we get this yellow line and we drain this pond. And if you look at the outlet of the pipe, you'll see that there's actually water running down this runoff path, and that water runs down all the way until it hits this pond. Well, if you recall, this pond can only hold so much water, and it's already it's already maxed out. And so what we're telling you here is that this pond is overflowing, and it is a condition that you as an engineer need to deal with. And so not only do we do the pipe sizing based on the headwater and basically our default optimal pipe size calculation. So in this case, for this 7 foot, for this about 7 cubic feet per second discharge rate, we calculated a 30-inch pipe would be needed, but we can see that 30-inch pipe isn't going to fit in the road, right? So we also have additional controls that we can use. So we'll use this outlet control HGS5, and that creates much smaller pipes with a different headwater value. And so to highlight what you're seeing in the scene here, this magenta line represents the maximum headwater elevation. So that magenta matches this magenta line here that gives you the maximum headwater elevation for the subbasin that you're in. And so that's as much water as this subbasin can hold until it overflows somewhere. This yellow line is the headwater elevation for this pond. So during the peak of the storm, the maximum depth of the pond is going to be at this tailwater elevation. So we're showing you that with this culvert design, that you are definitely not going to overflow this maximum volume, and so you've successfully drained the water away from that area. But then obviously we've created a little bit of a problem, because now we have additional water flowing into this pond. And so what that means is that you're going to have to deal with the tailwater volume that's coming down here. And so the reason why I point out the tailwater is you'll notice that we have, if you remember before, I said that the pond was already pretty much maxed out with the initial calculation in rainfall. You have to remember that we're looking at the peak of the storm at this point. So this is a snapshot in time. This is the most water that's going to be on the surface during the peak of the particular storm parameters that I put in for the storm event. And so what we're telling you here is if you put in that culvert pipe upstream, you're going to flood this lower pond. And this is how much tailwater that you're going to have to deal with. And the excess volume is essentially the amount of water that's going to be spilling over in this case. And even though we have a red gate here, and the red gate again allows us to control whether or not we want water to flow smoothly between two subcatchment areas to deal with these shallow ponds, what we can certainly do here is look at that and realize that it's only 735 cubic feet of water. That's really not a lot of water. Even in the peak of a storm, that's really not going to cause much of a problem. However, what can happen is that if the downstream, if it ends up flooding and you're going to get a downstream flooding event, you certainly wouldn't want to be putting in any structures around this area until you control this flooding condition. And so one of the ways that's easy to control this flooding situation, since we're all about culverts, is we can go ahead and we can draw a culvert across the road. And here you'll notice that I'm getting a yellow pipe, and that yellow pipe is really large. So we are dynamically sizing the pipe based on its location. And so what you'll notice is if I push the pipe way down here, it's not yellow anymore because the pipe slope is negative, meaning it's actually going to drain water. But the net effect is that this is a poor location for a pipe. And so this is an interesting way to use the pipe placement in P3D to figure out whether or not your terrain will support that pretty quickly just by visual inspection. And so we still have to deal with the water, the excess water in this pond, but again, because it's not very much water, the reality is it's probably going to evaporate and be absorbed into the ground anyway. So things to mitigate that would certainly be to ensure that there was a nice clear channel to flow along in here, and perhaps even put in a wider swale that would allow you to infiltrate a lot of that water during the storm, and then help to dissipate that just through evaporation and absorption. So let's go to a few other conditions here, and we'll just look around in the scene. And we'll notice this appears to be a fairly deep pond. So this pond is almost 16,000 cubic feet. So that's a pretty good amount of water. This is 5,000 cubic feet. So we're talking about, this is a small pool, and this is a very large pool of water. And so things that we can do to mitigate that is to attempt to put in culvert pipes to drain those. And so if we look at the elevation in this low point, we can see that's 261 by looking at the tool tips. And this is 262, so this is slightly higher. And then down here we have 261 and 259. So what's obvious is that if this is not going to be a buildable area out here, you can basically use that for detention, potential place to place a detention pond. And so what kind of a pipe would be required to drain this during this peak storm? In this case, we automatically calculate it's just a 9-inch pipe, so that wasn't too bad. And we have, and in fact, we have a little bit of allowable head in here. So you see that through our optimal calculation, which is turned out to be, the result was outlet gradually varied. So we automatically find the appropriate sized pipe to handle the storm. The blue outline here is the original pond elevation for the peak of the storm. Again, this magenta line is the maximum headwater that the topology of this subbasin can actually hold. And so what we're showing you here is that during the peak of this particular storm, if you place this pipe in here, the water will never come close to ever flooding. And so you've effectively controlled that. Now, if you want to allow more head, although a 9-inch pipe is pretty small, you know, in this case, you really would be okay with that solution. And what that's going to do is it's going to add volume to this lower pond. And what I didn't show you is that when I added that water, we get this orange tailwater. We get this orange boundary around the pond. So it went from blue to orange. And again, that indicates that you have a tailwater condition. And we're reporting the tailwater volume here of 1,343 cubic feet. So that's the difference between this yellow headwater for the design. That's the difference in volume between that yellow headwater and that blue pond elevation, which is the original pond elevation for this at the peak of the storm. And we report all of the design parameters in the tooltips. So when we talk about the max depth and the max volume for this pond, we're talking about the actual blue outline, which is the calculated maximum. And so down in this case, you don't see the blue outline because the tailwater is actually added volume to this pond. And so in this case, we've added about 1,300 cubic feet to this pond, and let's see, but it's also showing that the maximum headwater. So this is this magenta line. We can hold a lot of water over here if we want to sacrifice that. So essentially that means that we can add another pipe from the other side. And look at that. And so now what we've done is we've added an additional amount of tailwater. So now we're up to about 2,500 cubic feet. We have no excess volume because the pond can easily, the subbasin can easily contain that amount of water during the peak of the storm. And so now what we've done is we've ensured that in these two cases that the water will never rise beyond these yellow headwater elevations. And so it's your buildable area, and all of these ponds and headwater polylines are exported back to CAD as 3D polylines. So it's very easy for you to incorporate all of this design hydrology analysis information back into your CAD design, so that you know that you're not going to want to build driveways and certain things within this area. So there's some pretty safe places to put structures. And or it also tells you that this is an area that you need to do a little bit of grading to. And so in this hydraulic analysis can be useful to let you know that you're going to have to deal with grading in a particular area. But in this case, we know that we can deal with the water. If we want to make sure that we don't get any water or very much water, we can always play with the pipe sizing. And so we're in pipe sizing calculation mode, which is the default. And again, we have the Mannings, concrete or CMP. So typically this probably would be CMP anyway. And we would have a Mannings value of 0.025 associated with that. And you notice that as I changed the Manning, that it actually changed the diameter of the pipe. So all of these things are used, the pipe slope, the length, and the peak flow from the subcatchment area, which is a 17.924. When you draw a pipe in this subcatchment area, we automatically set the default discharge for that pipe for you to 17.94. You can modify this value. So you can say, well, I think that's going to be too much water. I really think it's only ever going to be 15. And at 15, we end up with a 21-inch pipe for this CMP. You can also decide that you really don't want to allow that much. So if you want to try to constrain the water to a much smaller area. So again, this magenta line is the maximum headwater for this basin. If you want to constrain that, what you can do is reduce the amount of headwater. And as you've noticed, that this yellow headwater boundary is shrinking. So what you're doing is increasing the pipe size, and by decreasing the amount of head. And so we can try for we'll try to go down one more to a foot. And obviously we've blown our pipe out. So what that tells us is this size of pipe would never do it. However, we do have the outlet controlled HCS5 method. And that typically produces much smaller pipes in a typical solution in the U.S. And what we can try to do is go down even a little bit lower. And what this is telling us is that the headwater depth just will not go below 1.53 with this amount of water at this allowable head with this slope. You basically just cannot drain any. You can't have a headwater any lower than 1.534. So if I put in 1.5 here, you don't get any change. So we have a nice 24-inch pipe that we can put in there. And what we've done is we've drastically reduced the amount of property that would ever be impacted during the peak of the storm. So this is the most water that's ever going to be stored in this area now based on this. So we've really reduced the amount of water, and we've also widened that distance between here. So if there's a driveway or some utility access or utility design corridor that's going to go through here, you've effectively kept the water from really super saturating that ground. So these are just a few tips on getting started with P3D to analyze your particular site and to use it as a tool to get a quick idea of any problem spots that may show up. So you can see lots of nice little roadside low points that are going to have to be dealt with in this particular project. And just in the same way that I dealt with all of these, you simply just continue the same process in connecting up your culverts and making sure everything just runs downstream. And if we impact a pond, it's certainly going to show you that you're going to have to deal with some additional pond water. And again, in this case, it's really not enough water to worry about. And in this area, it's looks like a good place to basically sacrifice some land, maybe even grade this out to be a formal detention pond, and then put control and outlet structures from that detention pond to go on downstream. So this is just a quick introduction to some of the quick roadside hydrology analysis and culverts placement and sizing routines that we have in P3D. Thank you.